So today's lesson is about heat and temperature, and we will continue speaking through the differences between those two terms. We'll talk about the three different scales in measuring temperature and the three methods of heat transfer. So we'll start with the difference between heat and temperature. So on a normal day, when you say something's hot, you assume that the temperature's higher. Or when something's cold, the temperature's lower. So heat and temperature are used interchangeably in day-to-day lives, in our day-to-day lives. In science, however, they're both two very different things. So when you say heat, you're actually referring to the energy, the overall energy in that substance. When you say temperature, you're only talking about the amount of vibrations or how quickly the particles are moving. So if you have, say, water molecules in water and you heat it up, what you're doing there is you're increasing the vibrations of the particles. You're adding heat energy to those molecules and they start to vibrate more and more and they move further apart. So you're increasing the temperature at that local section. Whereas heat, you have to look at the bigger picture. How many molecules there are. Very important. So if I have two frying pans, if I've got pan A and pan B, and in one of them I have 200 mils of water, and the other one I only have 100 mils of water. So this one has double the amount of the water in frying pan B. And if I am to measure the temperature at this section here, in both the pans, I find out that they're both 100 degrees Celsius. So the water's 100 degrees Celsius in both. That means that the temperature is the same, but the heat, very different. This has twice the amount of molecules as this, twice the amount of water. It's going to take you twice as long to heat up. How can we then say that the energy in both is the same? This has more water that's at that high temperature, so this has to have more energy. Think about it this way, in reverse. When you want to boil a kettle of water to give you coffee, you don't want to, if you're just going to get one cup of coffee from it, you don't want to fill the entire kettle up because you're going to stand there waiting for, 8-10 minutes. So what you want to do is just fill 200 mils of water and it's going to boil much quicker because you have less energy to give. You have less energy to spread through the water. Whereas if you fill it up, it's going to take you way longer because even though you're giving the same amount of heat, it's going to take you longer. So to make all those water molecules reach 100 degrees, you're going to have to keep giving the same amount of heat over a long time. So you're going to have so much more heat in this one than this one, even though the temperatures are the same. If you're confused, let's change the scenario. Let's say that the water in A is 50 degrees and the water in B is 100 degrees. This now means that the temperatures are different, but the heat is the same because this has twice the amount of water, but half the temperature. So technically, you've heated them up for the same amount of time. And the only reason why this temperature is less is because it's got more amount of water. So you've given the same amount of energy to both. You've given the same amount of energy to both, but this can only increase the temperature to 50 degrees because there's more to spread the heat energy over, and this goes to 100 degrees. Two very different concepts. Temperature is the local vibrations of the atoms and the molecules. Heat is the overall energy in that substance. So that's the difference between heat and temperature. Then we have these three scales. You've got the Fahrenheit scale, which America still uses today. You've got the Celsius scale, which Australia uses. And then you've got this Kelvin scale, which you learn about at university. I'm not going to talk to you about Kelvin yet. I'm going to speak to you about Fahrenheit. Fahrenheit is, there was a guy with the surname of Fahrenheit, and he said, I'm going to make 0 degrees the coldest temperature that I can make by mixing ice and salts. That is my 0 degrees. And I'm going to make my X degree human body. So we're at 37 degrees Celsius, but Fahrenheit said it was going to be, what was it? 96 degrees. So Fahrenheit said that the human body, I'm going to say, is 96 degrees. So he had his range. And then Celsius came along and he goes, hang on, why are we trying to confuse people? Some people might not have the same temperature, and when you mix salt and ice, it might not give the same temperature. It's not a good scale to link to. So he said, I'm going to say 100 degrees is when water becomes ice, and 0 degrees is when water becomes steam. Now this is confusing because you're like, no, 0 degrees is when water becomes ice and 100 degrees is when water becomes steam. Celsius said, no, 100 degrees is down there, 0 degrees is up here. And he called these centigrade. Centigrade, the word C-E-N-T-I-G-R-A-D-E. Centi means 100. Grade just means level. It's like I'm in grade 8, which is year 8. So he said it's, I don't know, 100 degrees centigrade means it's a 100-step process from 0 degrees, which he said is up here, to 100 degrees, which he said is down here. So that was really confusing, obviously, to all scientists. So after Celsius died, they said, you know what, we're just going to flip the situation. We're going to say 0 degrees is when water becomes ice, and we're going to say 100 degrees is when water becomes steam. Very simple. So that's the Celsius scale. Then a third guy came along and he said, no, because water can evaporate, not necessarily at 100 degrees Celsius, but it can evaporate at a higher temperature if you pressurize water. This is what we call superheating. So if you confine water and you heat it up, technically it can still remain as a liquid until 250 degrees Celsius. So it's called superheating. Then he said, because pressure still has an impact on the evaporating temperature of water, or the boiling point of water, I'm going to find a new point to relate to. And I'm going to call this 0 degree Kelvin. 0 degree Kelvin. He said, this should be the coldest temperature that you can ever achieve. So basically when the electrons stop spinning around the atom. And you achieve this in deep space, where there's no energy, no heat, nothing. And the atoms actually just freeze. The electrons just stop. 0 energy. There's no energy to actually activate the electrons. So he said this is 0 degrees Kelvin. And 0 degrees Kelvin is equal to minus 273 degrees Celsius. So we have to go down 273 degrees before 0 degrees, where water becomes ice. We have to go back another 273 degrees Celsius in order to reach absolute 0, which is 0 degrees Kelvin. You can't get any colder than this. So you can keep adding heat, you can keep getting hotter, blue hot, white hot, black hot, whatever, but you can't keep adding cold. Coldness doesn't exist. Coldness is just the absence of heat. You keep taking away heat, eventually you're going to come to a point where there's no more heat, so you can't make it colder. That's what 0 degrees Kelvin is. And we use this later on in physics at university. When we talk about any temperature, we start saying, yep, that's 30 kelvins, or that's, like room temperature is around 300 kelvins. So you stop saying around 20, 25 degrees Celsius. You just say, yep, the lab was 300 degrees kelvins. So you're going to get used to this later on. Those are the 3 scales explained: Fahrenheit, Celsius, and kelvins. Then you have the 3 methods of heat transfer. And the 3 methods, namely, are conduction, convection, and radiation. So the first one, we'll start with conduction. Conduction just means when you can't really move the atoms around. So like in an iron pole, you can't really move the atom places around like in water, where you can just put your finger in water and mix it. So in an iron pole, if you heat one end, eventually those atoms over there are going to start vibrating, and they're going to pass on their vibrations to the next bunch of atoms, and then they're going to pass it on to the next. So kind of like a domino effect. As the first one starts to vibrate, it passes on their vibration to the atoms further along the chain. So conduction is actually the movement of heat energy via vibrations in the atoms. But the atoms themselves don't actually move places. They're stuck in their place like bricks in a wall.